Okay, let's come to the first subsection, Lagrange Interpolating Polynomials. Okay, now here we need to consider another method to obtain the interpolation polynomial. Here, we just said, in order to obtain this function, polynomial function px, by these interpolation conditions, we need to solve this linear system to obtain the n+1 coefficients, right? But now we will learn another method to directly obtain the coefficients without solving this linear system. Then this is the Lagrange interpolation method. It's okay? So you should know, we don't like to solve the linear system. We want to construct the polynomial, interpolation polynomial directly. Okay, how to construct the polynomial directly? Let's come to the simple case from when the first case, when n equal to 1. That means we are given two function values, y0 and y1. We are given two nodes, x0, x1. Okay, so that means we are just given two data points. Then we need to find the straight line. This straight line is a linear function, right? And we know here x0 should be different from x1 because we know otherwise, okay, there is no existence and uniqueness, right? Okay, so we need to find a linear polynomial denoted by p1x, satisfying p1x0 equal to y0 and p1x1 equal to y1. Okay, here the subscript 1 means the degree. The degree of p is just 1. So that means p1x is a0 plus a1x is a linear function. But we don't like solve the linear system to obtain the two coefficients. Let's see how to obtain p1 directly. Now, because we know here by the geometric meaning, that means we just need to find the straight line. Okay, now we are given 2 points, x0, y0 and x1, y1. Then I think in your high when you are in high school, maybe you should know how to write the formula for this straight line determined by the 2 points. It's okay for you? Actually, we can consider the slope, right? The slope of this straight line can be represented by y minus y0 divided by x minus x0, right? For any point x, y lying on this straight line, then the 2 points from x0, y0 to x and y to this point, right? The slope is y minus y0 divided by x minus x0, right? This slope is equal to the slope of the 2 points x0, y0 and x1, y1, right? So the another slope is y1 minus y0 divided by x1 minus x0. Because they are lying on the same straight line, so they have the same slope, right? It's okay? So we move this term to right side, then move this term to the left side, then we obtain y minus y0 divided by y1 minus y0 equal to x minus x0. Change, right? X minus x0 divided by x1 minus x0. It's okay for you? This is the straight line formula passing through or determined by these two data points, right? It's okay for you? Then we have, that means P1 is equal to y. Then we need a clean here. It's okay. Now you see, that means y minus y0 equal to x minus x0 multiply y1 minus y0 divided by x1 minus x0. It's okay? Just multiply x minus x0 to this term. Okay? Now, we need to represent here. Now you see, continue, then we will obtain y equal to y0. Move this term to here, y0. Okay? Plus, okay, x minus x0 divided by x1 minus x0 multiply y1 minus y0. It's okay for you? Just move this term to here, right side, and move this term by this denominator here. It's okay? Continue. Let's consider. Now you see, separate the two terms. Then first term is x minus x0 divided by x1 minus x0 multiply y1, right? Multiply y1 minus x minus x0 divided by x1 minus x0 multiply y0. It's okay? And now here we have y0 here and also y0 here. So we compute the summation for these two terms. That means 1 minus, so by the denominator x minus x0, 1 means the numerator is also x1 minus x0. Okay, minus this term, minus x, minus plus x0. It's okay? And multiply y0 plus next term x minus x0 divided by x1 minus x1 minus x0 multiply y1. It's okay? And continue. Now you see, this x0 minus x0 plus x0 disappear, right? So what is left? Then for y0, this term numerator is x1 minus x, right? The denominator is x1 minus x0. Now we just change the order for both numerator and denominator. Then it is x minus x1 divided by x0 minus x1 multiply y0. Clear? And for this term also we just move to this term, x minus x0 divided by x1 minus x0 multiply y1. It's okay? So now we obtain, start from this formula to obtain y, now you see here y equal to, okay, a function of x numerator x minus x1 divided by x0 minus x1 multiply y0 plus x minus x0 divided by x1 minus x0. It's okay? Multiply y1. Clear? Then we obtain, okay, here, this function, okay, p1x, for x, now you see, just the degree of 1, right? So it is a straight line, or linear function of x. It's okay for you? Then we know. Let's check. This function p1x can satisfy here. Okay, we first check the interpolation conditions. Now you see, I write here p1x0. We substitute x by x0. So here is x0, right? Then p1x0, then here x0, here x0. Now you see this term disappear, right? And x0 minus 1, x0 minus x1, so it is just 1. Okay, so that means p1x0 equal to y0. Clear? And let's check p1x1. Okay, then here is P1 x1, then here is x1 minus x1, so disappear, right? x1 minus x0 divided by x1 minus x0, just 1. It's okay? So only y1. Okay, now you see P1x satisfies the two interpolation conditions. Okay, so we just check P1x, but now I want to write the formula of P1x in another form like this. Now you see, I write P1x equal to, we denote this ratio function, x minus x1 divided by x0 minus x1, denote by L0x. L0x, it is a linear function, right? X minus x1 divided by x0 minus x1. And also we denote this by L1x. X minus x0 divided by x1 minus 0. It's okay? Then we can write P1x by this L0x function, linear function, multiply the first function value at y0 plus another linear function denoted by L1x, multiply the second function value y1. It's okay for you? We just use different form, but now for this linear function, we call it by linear Lagrange interpolation basis. These two, L0x and L1x, at the two nodes x0 and x1. It's okay for you? I introduce you the new definition. Okay, new definition. So here, these two bases, L0x and L1x, we call them by the linear because they are linear function of x, right? Linear Lagrange interpolating basis at x0 and x1. Okay, so you should know what's the difference here. In the beginning, we can represent P1x by the linear polynomial just by a0 plus a1x, right? Then that means we use the two bases a0 multiply 1 plus a1 multiply x. That means we choose phi 0 by 1, phi 1 by x. We choose these two basis function. Then the two coefficients are a0 and a1. But now we change. We don't use the two basis function 1 and x. We use these two new basis function, right? Now you see x minus x1 divided by x0 minus x1. Here x minus x0 divided by x1 minus x0. Maybe you will think these two functions are more complex than these two basis functions, but don't worry about it. Okay, later I will show you why we like use this form, these two bases. It's okay. So, but firstly, you should know, understand. We can obtain this straight line by this formula. Okay. Actually, I show you the geometric meaning of the two basis function. Here is x0, here is x1, the two nodes. Okay, now let's consider the figure of L0x. Now you see, because if we check x0, L0, x0, that means the function value at x0, then it should be 1. It's okay? Because the numerator is same to denominator. Okay, so for example, this is function value at 1. Okay? And if we check the function value at x1, then here is x1. x1 minus x1 is 0, right? Function value is 0. Okay, now you see, because this is also straight line. Passing through these 2 points, then this straight line should be like this. It's okay? then this is L0x, the figure, the graph, right? And if we check L1x, then you see L1x0 is x0 minus x0 is 0, right? Okay, function value is a0. And if we check L1x1, then here is x1 minus x0 divided by x1 minus x0. So it is just 1, right? Okay, so that means these 2 points, okay, determine this straight line. So this straight line is the figure of L1x. It's okay? Now you should understand the geometric meaning of the two function functions L0x and L1x. Clear? These two straight line. Now you see, again, at x0, the two function values are special. For L0 function, its function value is 1. But for L1, the function value is 0 at x0. Okay? And at x1, they are also have special function values. Now you see, for L0, its function value is 0. But for L1, its function value is 1. It's okay? So, I can write these properties by this formula. So that means right here, Li function, okay, at xj function value equal to the two cases. If the two subscripts I and j, they are same, that means I equal to j, then the function value is 1. Now you see, here, L0, x0, it's okay? And if I is not j, is different, I is different from j, then the function value is just 0. It's okay? Now you see, L0, x1 is 0. L1, x0 is 0, right? Different. L1, x1 is 1. L0, x0 is 1. Clear? Satisfy this interesting property. It's okay? Of course, I will show you later for the other degree polynomial, Lagrange Interpolation Polynomials. They have the similar property like this. Okay? Okay, here, in a concluding, now you see here, L0, x0 equal to 1. L0, x1 equal to 0, right? And L1, x0 equal to 0. L1, x1 equal to 1. It's okay? So here, that means Li at xj equal to, when I equal to j, it is 1. Otherwise, it is 0. The function value is 0. It's okay? You say different, 0, 0. Same, 1 here. Okay? Okay, now, by these 4 properties, formulas, then we can check P1x satisfies the following interpolation conditions. P1x1 equal to y1. P1x0 equal to y0. It's okay? So we call P1x by the linear Lagrange Interpolation Polynomial. It's okay for you? Okay. Here we check these two properties by substitute x by x0 and x1. It's okay? Now we check this property by these 4 formulas again, because now you see we write P1x by L0x multiply y0 plus L1x multiply y1. It's okay? 2 bases, 2 function values. It's okay? Then if here we use P1x0, then here is 0, here is 0, right? x0, x0. Now you see, by this property, L0, x0, they are same. So it is 1. L1, x0, the 2 scripts are different, then it is 0. So in this case, equal to y0. It's okay? And if we check P1x1, then that should be L0x1 multiply Y0 plus L1x1 multiply Y1. Now you see it should be Y1 because this term here is 0, but this term is 1. Clear? So that means these are very important properties. Interpolation properties. It's okay? Okay, so next we will focus on these properties to construct the two bases, okay? Okay, let's come to the case n equal to 2. That means we are given 3 points, x0, y0, x1, y1, and x2, y2. Now, we don't like to solve the linear system. We want to construct the polynomial directly. Of course, you should know the 3 nodes are different, right? They are different nodes. Now, we need to find a quadratic polynomial denoted by P2x such that P2x0 equal to y0, P2x1 equal to y1, and P2x2 equal to y2, right? The 3 interpolation polynomials conditions. Okay, now we write P2x in the form L0x multiply y0 plus L1x multiply y1 plus L2x multiply y2. Now you see we don't write it in this form A0 multiply 1 plus A1 multiply x plus A2 multiply x squared. We don't use this form. We use this form. Now you should understand. Now you see y0, y1, y2 are the 3 function values. We are given the 3 function values. So for each function value, we multiply a function denoted by L0x, L1x, and L2x. It's okay? It's okay? So the question is how to determine the 3 functions L0x, L1x, and L2x. It's okay? Now you should understand here these 3 functions Lix, they are the quadratic Lagrange interpolation basis. Why we call them by quadratic Lagrange interpolation basis? Because they satisfy these following properties. Okay, now you see L0 at x0 by the same subscript, then the function value is 1. L0 x1 different subscript 0. L0 x2 0. L1 x0 0, right? Different. L1 x1 same subscript 1, right? And L1 x2 should be 0. It's okay? L2 x0 different 0. L2 x1 different 0. L2 x1 same, right? It is 1. It's okay for you? This is also this property Lixj equal to if I equal to j is 1. Otherwise, the function value is 0. Clear? Again, we can use this property. It's okay for you? Of course, I show you the figures of the 3 functions. For example, L0, you see, at x0, its function value is 1. So here, it's okay? And at x1 and x2, they are 0. Okay, 0, 0. So you see, the right line is the parabolic curve of L0x. It's okay? The right curve, parabolic curve. And for L1 at x0 is 0. At x1 is 1. Now you see, now we choose this point is x0, this point is x1, this point is x2. Okay, just use the numbers by 0, 1, and 2. Okay, now you see L1 x1 equal to 1. Okay, L1 x2 equal to 0. So the green curve is the figure of L1x, another parabolic curve, right? Okay, next, L2x0 is 0, L2x1 is 0. So you see, the blue curve, 0, 0, this point is 1. Okay, so the blue curve is the function L2x. You see, it's very beautiful, right? Okay, the three polynomial functions, right? They are quadratic Lagrange interpolation basis. It's okay for you? The three parabolic curve. Okay, so L0, L1, and L2. Clear? Okay, now I just show you the figure. We don't show you the representation or the formula for the three functions, right? Now, I show you how to determine the three functions one by one. Okay? So, let's consider L0x. For L0x, we are given the three conditions. Now, what does it mean for the last two formulas? Now you see, it means x1 and x2 are two 0 point or roots for L0x. It's okay? So that means by this condition, two conditions, that means L0x, it is a polynomial, right? Because it has two roots, x1 and x2, then it should include the factors x minus x1 and x minus x2. Clear? Because they have the two roots, x1 and x2. Now you see, this product is already a quadratic polynomial. So here should be a constant. The difference between the two quadratic polynomial should be a constant c. And how to determine the constant? Now we have this condition. L0, x0 equal to 1. So if we substitute x0 here, then here is x0 minus x1 multiply x0 minus x2 multiply this constant should be 1. Then we know this constant is 1 divided by the two terms. Clear? Then we can know L0. Okay? Now, let's show you the details. By the two conditions, we are know. Okay? x1 and x2 are two roots of L0x. So, this function should contain the two factors x minus x1 and x minus x2, right? We only need to determine this constant. Now here, we use a. Okay? A is constant, right? A constant. Now, we have this condition, L0, x0 equal to 1. So that means here, 1 equal to a multiply x0 minus x1 multiply x0 minus x2. Of course, we know a should be 1 divided by x0 minus x1 multiply x0 minus x2. Clear? Then come back. Then we can know L0x, this function is equal to, okay, the numerator is x minus x1 multiply x minus x2. The denominator here, you see, x0 minus x1 multiply x0 minus x2. It's okay for you? The computation, right? Okay, now I show you how to remember this function. Here, L0, then you see the denominator, the numerator, firstly, the numerator is the factors, okay, conclude, x minus other nodes. We have three nodes, right? Here, 0, then other nodes means x minus x1 multiply x minus x2. This is denominator, numerator, sorry. But for the denominator, it is very simple. Just replace x by x0. So you see, from x minus x1 to obtain x0 minus x1. From x minus x2 to to x0 minus x2. It's okay for you? So it is very easy to remember, right? Okay, so by this rule, you can guess L1x. Okay, it should be a ratio. Firstly, it should be a ratio. And what is the numerator? Now, because here is 1, okay, for other nodes should be x0 and x2. So the numerator is x minus x0 multiply x minus x2. It's okay? And what is the denominator? Remember? Then just replace x by x1. You should know the subscript here, 1. So replace by x1 minus x0, replace x by x1 minus x2. It's okay? Then we obtain L1x. Now you feel it is you find it is very simple to remember the formula, right? Of course, practice. What is L2? Okay, again, it should be a ratio, right? The numerator is x minus other nodes, the factors. So here is 2, then other nodes are x0 and x1, right? It's okay? Then what is the denominator? Denominator is just replace x from numerator by x2, the same subscript. It's okay? So x2 minus x0 multiply x2 minus x1. It's okay? So then we obtain the 3 basis function, L0, L1, and L2. They are the quadratic Lagrange Interpolation Polynomials. It's okay? The basis. Then by the 3 bases, then we can obtain P2. P2 I write here firstly. P2x is just L0x multiply y0 plus L1x multiply y1 plus L2x multiply y2. It's okay? And now you see, for the function values y0, y1, y2, for each value, multiply a basis. Okay, now you see, this index is 0, then this is L0. What is L0? Again, the rule. The numerator is factors with x minus other nodes. So here 0, other nodes x1 and x2. Then replace x by x0 to obtain the denominator. It's okay? And for y1, then the numerator x minus other nodes x0, x2, right? And then replace x by x1 and x1 to obtain denominator. Clear? So for y2, okay, numerator x minus other nodes 1, 0, right? And divided by denominator, replace x by 2, 2, 2. Okay, clear? So now you see, it is very easy to remember the function, right? Okay, of course, I will show you. Actually, we obtain L0x by the 3 conditions. It's okay? Of course, we can check this function. For example, L1x can satisfy. Now let's check here. L1x0, the function value. Now replace x by x0. Now you see, this term is 0, so the ratio is 0, right? And L1x1, now you see, if we replace x1, now you see, we have same numerator and the denominator, so the function value is 1. It's okay? And let's check L1x2. Okay, now you should know, for x2 here, x2 here, x2 here, now you see, this term is 0, right? So 0. Clear? Clear? Of course, you can check for L2. Satisfy L2x0 equal to 0, right? Because we have this term. L2x1, then x1 minus x1, 0, right? And L2x2, then x2 minus x0, same. x2 minus x1, same. So the ratio is 1. It's okay? So on the contrary, we can check for the 3 basis functions like this, satisfy these 9 conditions, properties. It's okay for you? Okay, now I show you the two sample case when n equal to 1, we obtain L0 and L1. The two bases satisfy these properties, right? And for n equal to 2, we know the three bases, okay, satisfy this property again. Now you see, this same properties. Okay, so next, we can consider the general case. For the general case, now we are given x0, x1 to xn, n plus 1 different nodes in an interval AB, right? Then we need to determine Ljx is the basis, right? The basis Ljx. So firstly, you should understand it is a ratio, right? What is the numerator? What is the numerator? Right, because the index is j, then the numerator conclude the factors x minus other nodes, right? So you see x minus x0 multiplied to x minus xj minus 1, right? Then x minus xj plus 1, because this is j, so we don't have x minus xj in the numerator, right? Then multiply to last term x minus xn. It's okay? This is a general case. Now, how many terms, factors here? From 0, j minus 1 to j plus 1 to n, we have n terms, right? So, n degree. Clear? Okay, this is numerator. How to obtain the denominator? Okay, very simple, right? Just replace x by xj. So, xj minus x0 multiply xj minus xj minus 1, xj minus xj plus 1. Because there is no x minus xj in the denominator, so we don't have xj minus xj in the denominator. It's okay for you? Okay, last term is xj minus xn. Clear? This is Ljx. Okay, if you remember this rule, okay, you can construct the Ljx directly. Now see, we don't need to solve the linear system. We just write the basis function directly. If you remember the rule, then you can write the basis. You don't need to solve the linear system, right? Because we choose the Lagrange Interpolation Polynomial like this. It's okay for you? This is the advantage for Lagrange Interpolation basis. Okay? Okay, and here I show you another form. Of course, this is additional result. If we denote Wn plus 1 by x minus x0 multiply x minus x1 multiply to x minus xn. Now you see we have n plus 1 factors. So this is degree. The degree is n plus 1. The polynomial is n plus 1. So now you see without x minus xj in the numerator, that means we divide x minus xj. It's okay in the denominator. And these terms, okay, can be represented by the derivative. Okay, here should be n plus 1, the same function, the derivative of the same function at xj. Okay, of course, for you, it's better to remember this form. That's okay. If you cannot understand this form, that's okay. But this one is necessary for you. Okay. Now, by check, we can know Ljxi. We replace x by xi. So now you see, if xi is same, the index is same with j, I equal to j. Now you see, we have same numerator and denominator. So the ratio is 1, right? It's okay. Otherwise, now you see, if I is different from j, okay, at least one term of the numerator should be 0, right? So the ratio is 0. Clear? You see, again, we use this property. Okay, ij from 0 to n. Okay, so now you see, generally, we call Lj by the Lagrange interpolation basis of degree n. Oh, here we don't use I, okay? Function Ljx, okay? are the Lagrange interpolation basis of degree n, j from 0 to n plus 1, n plus 1. Clear? Okay, so this is a famous and popular Lagrange interpolation method by polynomial of degree n. Okay, then now you see Pnx is a polynomial, okay, equal to the summation of a function value yi multiply every basis yi, Lix, right? Then we know this is unique polynomial in the space of polynomial of degree at most n, satisfying the interpolation conditions Pnxi equal to yi. Clear? Okay, so then we know Pn is called the Lagrange interpolation polynomial of degree n. Okay, here Li, Lj, they are bases. Okay, they are also polynomial of degree n, right? Okay, then we know. Okay, some notes. Okay, here you should know the number of bases. Okay, I from 0 to n plus 1 is the same to the number of nodes, right? The nodes are x0 to x1 to xn. Okay, the sum of number of bases is same to the number of nodes. And the degree of the polynomial is the number of nodes minus 1, because we have n plus 1 nodes. The degree is n. It's okay? And the interpolation basis guarantees the interpolation polynomial to satisfy the interpolation conditions. It's okay for you? By these properties. Now you see, by these properties, it's okay? Then we can obtain the interpolation conditions are satisfied. Okay, and also you should know, the interpolation bases are independent of the order of nodes. It means here, you can denote, here is x1, here is x2, here is x3, here is x4, here is x5. It's okay, right? We don't care the order. We don't care the order of the nodes, because now you see, they are product, so you can change the orders. It's okay? So here, that means the interpolation bases are independent of the order of nodes. It's okay? Okay, so this is a famous Lagrange interpolation method. Okay? Okay, and also here is a interesting and important property for the Lagrange interpolation basis. They satisfy the partition of unity. That means the summation of the basis equal to a constant, just 1. So that means unity, partition of unity. It's okay for you? So you firstly understand the meaning. The summation usually not, you see, that means L0x plus L1x plus 2 Lnx, because they are n plus 1 functions, polynomials. Usually, okay, for arbitrary functions, the summation should be also a function. But the special meaning here, the summation is equal to 1 constant 1, not function, just a constant. So very, very important property. We call it a partition of unity. Okay, why we have this property? Okay, I show you the reason. Because for any n plus 1 different interpolation nodes, x0, x1, xn, right? Okay, now if we just consider all the function values are 1, yi equal to 1, I from 0 to n, that means we are given here, right here, x1, x2 to xn, the function value 1, 1, 1, just 1. Okay, then you see, of course, we can find the constant function, just 1, to satisfy the interpolation conditions. Okay, then by the uniqueness by the uniqueness of the interpolation polynomial, we have, okay, just one. Now you see constant function, just one. Okay, so that means Li x summation, we can multiply 1. This 1 means the function value for each node, okay? And 1 is the yi, for each value is yi, right? So now this is a Lagrange interpolation function Pnx. So we know Pnx just the constant function 1. So the summation of Li is constant 1. It's okay? So this is a partition of unity of Lagrange interpolation basis. This property can make the Lagrange interpolation is very useful in geometric design. Okay, so this is another topic. Okay? Okay, at last, let's consider an example. Now, we are given the following function values of fx, an unknown function, okay, or complicated function. We don't know the formula of fx. We only know several discrete points. Now, you see from for xi equal to 1, 2, 3, and we are given the three function values are -1, and 1. It's okay? So I show you the figure 1, 2, 3. Okay, -1, and 1. For example, okay, -1 should be here. -1, and 1. Okay, here this is x, and here is 0. Then here is y. It's okay. Then now you see that means we need to find a parabolic curve like this. Okay, satisfy the three conditions, passes through the 3 points. Okay, now we don't solve the linear system as the beginning. We know we can directly write the functions, right? Okay, now we find because there are 3 nodes, so the number of nodes -1 is the degree of the polynomial, right? So quadratic polynomial denoted by P2x. Okay, then if we find P2x, then we can approximate f function value at 1.5 by using P2x, right? Okay, so now firstly, let's practice. We determine the Lagrange interpolation basis, 3 bases, right? Okay, L0x, let's practice. Please follow me, okay? It should be a ratio, right? What is the numerator? The numerator is x minus other nodes, right? So for L0, okay, so you should, because here we use 1, 2, 3, and so x0 is 1, x1 is 2, x2 is 3. It's okay? I just show you the discrete points. So for L0, then should be x minus other nodes. So x minus, because this is focused on x0 is 1. So for other nodes, they are 2 and 3. So directly here, x minus 2 multiply x minus 3. It's okay? The numerator. What is the denominator? Denominator just replace x by x0. Here, x0 is 1, right? So it is 1 minus 2 multiply 1 minus 3. Clear? You should understand the rule. Then you can write it quickly, right? Okay, actually, you see, 1 minus 2 is minus 1. 1 minus 3 is minus 2, so the denominator is 2. So 1 over 2 multiply x minus 2 multiply x minus 3. It's okay? Simple function, right? Okay, let's come to L1. L1, so what is L1? X1 is 2. So for other nodes are 1 and 3. So the numerator is x minus 1 multiply x minus 3. Okay, denoted by replace x by x1. You should know x1 is 2 here. So 2 minus 1 multiply 2 minus 3. It's okay? So 2 minus 1 is 1, 2 minus 3 is minus 1. So it is minus 1 multiply x minus 1 multiply x minus 3. Clear? See, it's simple, right? Okay, last, L2. Okay, for x2, other nodes are 1 and 2. So x minus 1 multiply x minus 2. Then replace x by x2. You should know x2 is 3 here. So 3 minus 1 multiply 3 minus 2. Clear? Okay, now 3 minus 1 is 2. 3 minus 2 is 1. So the the denominator is 2. 1 over 2. Multiply x minus 1 multiply x minus 2. Clear? Now we know the 3, so we obtain the 3 bases. So for each basis, multiply the function value one by one and compute the summation. Then we obtain P2x. Right? It's okay? So I write here firstly, P2 should be, okay, y0 multiply L0x plus y1 L1x plus y2 multiply L2x. Clear? So y0 here, y0 is minus 1. So it is minus 1 multiply this function at 0. And y1 is minus 1. So another minus 1 multiply this L1. And y3, this is y1. And y2 should be 1, right? So multiply this function. Then compute the summation. Clear? Okay, so now you see, then we obtain P2x equal to L0 x multiply y0 plus L1 x multiply y1 plus L2 x multiply y2. So L0 multiply y0 minus 1. L2 multiply y1 another minus 1, sorry, okay? And L2 multiply y2, it is 1. Okay? Now you can compute the summation. Okay? So at last, I just show you the result. Okay? Please practice. I show you the details here, but I don't have enough time to explain you in details. So I just show you the final result. The final result is x squared minus 3x plus 1. It's okay? Then we obtain P2. Of course, when you obtain the P2x, please check. Let's check P2 at minus 1, right? Here, P2 at 1. What is the function value? 1 minus 3 plus 1. So it is minus 1, right? It's okay? Satisfy y0. And if we check P2 at 2 is x1. Okay, 2 squared 4 minus 6, it is minus 2 plus 1. Okay, minus 1 again. Right? It's okay. Check the function value. Okay, at last, let's check P2 at 3, right? P2 at 3. So 3 squared is 9. Minus 3 multiplies 3. 9 minus 9, 0 plus 1. So it is 1. Right? You see? Check. The function value here is y2 is 1. Now, we checked the 3 conditions. So this is a unique quadratic polynomial, right? P2. Okay, that means we can use P2x to approximate the function fx. Now, if we want to find the approximate value of f at 1.5, then because we know the sample function P2, so we can directly compute P2 at 1.5. Then that means 3 over 1 square minus 3 multiply 3 over 2. 3 over 2. Okay, plus 1. Then you can obtain the answer is minus 1.25. That means we can use this value to approximate the unknown value. It's okay? So this is interpolation approximation. Interpolation means we are given the discrete point, right? We can find here I show you the figure again. What is interpolation? Here you see, interpolation approximation means we are given several discrete points. We find a simple function px. Okay, polynomial formula, for example, then interpolate these points Now, then we can use this simple function to approximate this complex or unknown function. It's okay? So this means interpolation approximation. It's okay?